All right. Hello, everybody. This is Club A. My name is Keith. I'm the president of the Ethical Hacking Club at McEwen University. And today we're going to continue our Introduction to Capture the Flag series of videos. Today we're going to be covering the topics of cryptography, password cracking, and log analysis. It's a lot of topics, but just keep in mind the purpose of these presentations is to just introduce you to the ideas that are used in cybersecurity and capture the flag competitions. Hopefully later on we'll get a chance to dive a little bit deeper, and if you stick around after the presentation in our Discord channel, you'll be able to help us and work with us through some challenges. So the first topic tonight is cryptography. So what is cryptography? Cryptography is the method of hiding secret messages through text or through signals. One of the oldest cryptography methods is called the Caesar cipher. It was supposedly made by Julius Caesar, who was a emperor in ancient times. Anyways, a long time ago. So a cipher is essentially an algorithm for decrypting or encrypting a message. In the case of the Caesar cipher, we're substituting one letter for a new letter. Here's an example of the Caesar cipher. At the top, we have the ciphertext. In the center of the screen, we have a picture of the key. And at the bottom of the screen, we have an equation that represents the encryption of the message. So what are we looking at here? EX equals X plus 7 mod 26. What does that mean? EX is the encrypted message. X plus 7 mod 26 means that we have X, which is our plain text, and 7, which is the key. What the Caesar cipher is a substitution cipher, and what we do is we shift the alphabet by 7 in order to decrypt this message. So if we look at the outer wheel, we can go to the first letter, which is D. Or sorry, we go to the inner wheel, which is the encryption, and we go to the D, and we decrypt it to W. We do the L, we go around to the L, it decrypts to E. We do the S decrypts to L, and on and on and on. And you can decode this message yourself to see what it is. Essentially, what we have is in this equation, we have the ciphertext, the plain text, and the key. These are how we describe encrypted messages. It's called cryptanalysis. Now, this is a very simple cipher, and one of the most ancient ones. There are other common types of ciphers. We already talked about the substitution cipher. There's transposition ciphers, polyalphabetic ciphers, polygrammic ciphers. You don't really need to know how every single cipher works to get started with these, just generally how they work. So if we look at these pictures, we can see in the top the what's known as the pigpen cipher. At the top, we see the symbols, and underneath it, we have the key to decode that particular cipher. The alphabet is divided into 3 kind of tic-tac-toe squares, with each corner of the tic-tac-toe box representing how it would be encoded in Pigpen. So we see the first letter in the ciphertext is a left-facing box with a dot in the middle. That decodes to M. There's lots of different symbolic and substitution ciphers that we can talk about. Another common one is called the rail fence cipher. Here we see the plain text. This is a secret message. The rail fence encoding is given a key of 4. This means you draw boxes 4 deep or 4 down. You then type the message in, going diagonally on the box till you hit the bottom, and then come back up and down and up and down and up and down. Then to record the ciphertext, you just record each row sequentially. So the first row, the second row, the third row, and the fourth row. That is how you do the railfence cipher with a key of 4. There's also constructed scripts and languages that are used as substitution ciphers. People often use similar principles as the Caesar cipher, but instead of shifting the alphabet, we see different symbols representing letters. Depending on which language you're decoding to, these ones all decode to English. You can have fictional languages, constructed scripts, or hieroglyphs to represent messages. I think the text at the bottom is from Lord of the Rings. On the right here, we have the Skyrim dragon tome speak. I think to the left of the Skyrim stuff is some Vulcan, and up top are some Egyptian hieroglyphs. These all represent ciphertexts. There's some awesome online tools that you can use to check out other ciphertexts and also identify which cipher you're looking at if you have a string of text to look through. My favorite tool is this decode.fr. Don't worry, I'll be sharing the slides in our Discord server if you want to look at them. There's also CyberChef, which is put out by the GCHQ, which is the British intelligence wing. And there's also a box and trick, which helps you identify ciphers as well. These online tools will help you recognize what kind of cipher you're looking at, and will actually perform cryptanalysis for you to determine what the most likely cipher is that you're looking at. Very useful tools. Just briefly, I want to talk about encoding. So last time in our video, we were talking about network traffic analysis. This is essentially the same idea behind encoding, okay? So we can have binary encoding, which is essentially the electricity running across the wire. We can have base 64, which is a common web-based encoding. Hexadecimal, which is a base 16 form of representing numbers and letters. We have the decimal representation, which is technically an encoding, but this is just a really big, really big number. Let me go back. Sorry about that. And then we also have like character sets like UTF-8 or ASCII. There's many more, Unicode. These are just ways of translating one form of text to another, kind of like a substitution cipher. And these are very useful for computers to use. In modern encryption, we talk about two different crypto systems. We have symmetric crypto systems and asymmetric crypto systems. The symmetric crypto system works by the sender and receiver having the same key for the message. So as you can see in this diagram here, the person on the left, I, has some data. He uses this key to create a cipher from that data. Then you use the same key to decrypt that cipher and be able to read the data. That's called the symmetric key crypto system. Basically, it's the same key is available to both parties in the communication. Asymmetric crypto systems, a good example of that is public key cryptography. We use public key cryptography every day in web communication. So essentially how public key cryptography works is you have the key generation for Alice. Alice takes a big random number, plugs it into the key generation function. The key generation function gives Alice a public key and a private key. So when Bob wants to send Alice a message, Bob can encrypt his message with Alice's public key. This gives a ciphertext. The ciphertext is then sent to Alice. Alice is able to decrypt that key with her private key. That's an example of asymmetric crypto systems. Now, this is a very, very broad overview of encryption. Let me just preface this. If it's not exactly crystal clear, the point is to just introduce you to the ideas. We've gone from the Caesar cipher, which is a simple substitution cipher, to different crypto systems that we use in our everyday communication on the internet. So, why is it that we actually know all of this cryptography? Wouldn't it make more sense if the cryptography was kept secret? Like, why do we have to know how these crypto systems work? The strength of the crypto system shouldn't lie in the secrecy of the algorithms to create the ciphertext. The strength of the system should depend on the secrecy of the key. And so, what that means here is that no one is going to be able to take Alice's public key and get the private key. Unless someone has intercepted the symmetric key, they're not going to be able to get that symmetric key. That is the idea behind modern encryption, is that the strength of the algorithm is the secrecy of the key. And this is very important because coming up soon, we're going to have a introduction of a disruption to modern cryptography with quantum computers. But in capture the flag competitions, cryptography is going to have you look at challenges that go anywhere from Caesar cipher and substitution ciphers to fixing a wrong implementation of like RSA, a public key crypto system. So that's just kind of a brief introduction to cryptography. It's super, super brief, and it's a very in-depth topic, very math heavy. Obviously, a lot of it revolves around obscure number theory. So I'm not an expert in this at all. In fact, I would say this is probably one of my weaker categories. But cryptography is so important to at least understand the basics. You want to know what a ciphertext is, you want to know what a key is, and you definitely want to know what the plain text is in the context of a capture the flag, because that's usually what the flag will be when you finish the challenge. And when we get to the workshops later tonight, we'll be going through that. So the next topic we're going to move into, I just want to do a brief review, kind of introduction of the idea of hashing. So if you haven't taken a data structures and algorithms course, you might not be familiar with what hashing is. Essentially, what hashing is a way to uniquely identify a specific object from a group of similar objects and map it into a array. Essentially, what you want to do is come up with a function that's going to convert one element into an integer, which is going to be the index of the array, and store that element in the array. The best sort of hashing algorithm is going to create a uniform table of elements, which will allow you to very quickly look up the elements in that list. And ideally, there's no collisions. So if we look at this example that I stole from Geeks for Geeks, we see we have an array of 11, 12, 13, 14, and 15, and a hashing function that takes each element of that list modulo 10 to get the key. It then puts it into this hash table, which is the map that I was talking about. So we have 11 mod 10 gives us an index of 1, 12 mod 10 gives us an index of 2, and on and on and on. This particular hashing function is actually bad, I guess, because what would happen if instead of 12 we had 21? We would have the same value mapped to 1. So this is just important to know because we've gone from talking about cryptography, and this next topic is password cracking. In order to understand password cracking, I just felt like it was necessary to talk quickly about hashing. So with cryptographic hashing, it's going to convert one numerical input into another. The output of the hash function is always going to be the same length, and the values that they return are called the digests. Or if we're looking back at that hash table example, the message digest would essentially be the key. Effective cryptographic hash functions have the following properties. They're computationally hard, if not impossible, to reverse. You cannot generate the same hash by two different inputs. So, like we looked at in the previous example, we don't want two inputs mapping to the same hash. The reason why we don't want that to happen is because if you set your password to one value and it turns into a hash, and someone is able to make a completely different password that matches that hash, essentially they're able to get that password without knowing that password, if that makes any sense. So cryptographic hashing, the hash function has to be collision resistant. A small change in the input of a cryptographic hashing function should result in a drastic change in the output. Like if you just change one letter, it should change pretty much the entire look of the hash. Another important cryptographic hash property is that it's fast to compute. It's not computationally expensive to create the hashes. So I highly recommend, if my explanation didn't make a whole lot of sense, which I don't think it did, but if it didn't make a whole lot of sense, check out this video on the Computer File YouTube channel. Great channel. And it should kind of get you thinking about what a good hashing algorithm or hashing function would be. So typically what we use cryptographic hashing for is for password storage. Obviously, we're talking about password cracking. Passwords aren't stored in their plain text form. They're stored in their hash form. So it's difficult for anyone who finds the hash to be able to decipher it. Because remember, cryptographic hashing is meant to be one way only. It's also good for a data integrity check. I don't know if you've ever downloaded any file or any operating system and they say, check the SHA checksum to make sure. Well, that just makes sure that the data that you're getting is the same data that they promised to give you. If anything was changed in that data, the hashes would be different. Because, again, the properties of cryptographic hashing, they don't have collisions, or they're collision resistant. Although, historically, we have created cryptographic hash functions that have been broken. And we'll talk
Let's
about
say you want to try.
did not mean to hit play there. So typical cryptographic hashing, like the most popular ones you're going to see are the secure hash algorithm, well, also known as SHA. There's three separate families of it: SHA-1, SHA-2, SHA-3. SHA-1 has been broken. So essentially what that means is they're able to generate the same hash using different values. So it's not just able to be broken by finding out your password, but if you find a SHA-1 hash in the wild, there's actually cryptographic attacks that you can do on it to break it without using a password list at all. There's also message digest, like MD2, MD4, MD5, MD6. Again, anything less than MD5 has already been broken. And then there's also the Windows NT hash, NTLM, it's known as, and that's also an interesting one with weaknesses as well. So when you're looking at a password cracking challenge in a CTF, the most handy thing I've found is being able to identify the cryptographic hash just by looking at it. So your MD5 hash is going to be 16 characters long. Your SHA-1 hash is going to be 20 characters long. Anything in the SHA-2 or SHA-3 family of hash functions is going to be 28 to 64 characters long. And the NTLM hash is actually two separate hashes jammed together, and both of them are 16 characters long. So each hash is essentially MD5, as far as I understand it. I could be wrong, could be completely wrong. If I am wrong, please let me know. I would like to correct any bad knowledge I might have. That's kind of the point of this. So here's what they would look like. So as I said, the MD5 is going to be. Sorry, I thought I could highlight there. The MD5 is going to be 16 characters long. The SHA 1 is 20. SHA 256, that's part of the SHA 2 family. I'm pretty sure this is one of the longer ones. And then NTLM is going to be 32 long. Something that we haven't talked about is SALT. So basically, a SALT is another way to make your cryptographic hash function work a little bit better, or make it more computationally intensive to decrypt the hash. What it does is essentially you're taking the plain text, adding a little bit extra to it, and then putting it through the cryptographic hashing algorithm to get a brand new cryptographic hash that will hopefully deter attackers or anyone to try and decrypt it. Of course, I've only just mentioned the most common ones. There are lots and lots of cryptographic hashes. We've got, in this particular list here, we've got MD5 crypt, bcrypt, PDF password hashes, and on and on and on. At the bottom of this slide, we've got a reference to the Hashcat website where they talk about example hashes. Later in the workshop, we're going to go through Hashcat and talk about all the different functionalities that it can do. But I don't want to talk too much about these because I think tonight we're just going to be working on the most basic password cracking. And we also have, I think, 2 videos already on our YouTube talking specifically about password cracking. So password cracking is kind of a funny term. It just means that you're decoding the hash of a password. So we just do essentially what we just explained you're not supposed to be able to do. How are we able to do that? Well, unless it's the case of SHA-1 or MD5, passwords are usually easier to guess and verify against the hashing function than it is to brute force reverse a hash without guessing. Password cracking refers to rapidly generating password hashes from a list of words until you find a hash that matches. So if you have a hash of a password, you know that the password is either in a list somewhere or you have some idea of what that password could possibly be. If you run a list of those words through that hashing function, you could possibly find a match. And that's what we're doing when we're doing password cracking. A lot of CTFs are going to ask you to recognize, obtain, and crack password hashes. So we're going to take a look at a couple of the tools. The first tool that we would like to take a look at is called Hashcat. Hashcat allows you to do multiple different attacks. You can do the brute force attack, combinator attack, dictionary attack, rule-based attack, toggle case attack. Essentially, if you want to see all the options available to you, you can type in the help option when you're using Hashcat. And at the bottom of the slide here, we've included a couple common examples. So the first example there is a brute force attack against, I forget what the 3200 code is. I think it's a form of SHA, or it might be bcrypt, actually. Anyways, if you run hashcat-h, you'll get the table to look up what that is. And so what we're doing is we're running the -a, which is the attack mode, 3, which means brute force, against the hashes.txt, which is, in this case, a list of hashes. And what we're doing here is defining what we're brute forcing. So in this particular challenge, we were given kind of an outline to what was in the password. And with Hashcat, you're able to do a brute force to determine what the password is. So here, these $A, $A, $A represents capital alphabetic characters. So capital A, capital B, on and on and on to capital Z. And in the end, these question mark Ds represent digits. So anywhere from 0 to 9. So essentially what the challenge was asking you to do was to brute force the values because you already know how the password is constructed. Knowing how a password is constructed helps you create a list of words to try to brute force against that hashing algorithm to find a match. And once you find a match, because we know the properties of the cryptographic hash algorithm or cryptographic hash function, cryptographic hash functions, we know that that is the actual password. You can also run a word list attack against it. This is different than the brute force in that it runs a list of passwords against the hashes and runs it through. So M500, I believe, is MD5 or maybe it's SHA-1 in Hashcat. It's one of the common ones. -A means you're doing the word list attack. Hashes.txt, that's the same list of hashes as before. And then you're running RockU. RockU is one of the largest password breaches that's widely available for people to download and use. And it actually comes pre-installed on Kali Linux. So if you've got Kali set up, you can use RockU with these programs to just try it out. Hashcat also allows you to do a rule-based attack. So here you can see in the options, -M0, I believe, is MD5. -A is the attack mode. We're doing the word list, but we're adding on a rule. So in this particular case, we're adding the one rule to rule them all rule, which is kind of a bad idea to do because essentially what a rule-based attack is going to do is add rules to your words. So for each word in RockU, it's going to try adding like digits before, digits after, uppercase, lowercase, leet speak versions, all different versions of each word in RockU. And I'm pretty sure RockU is over 1 billion entries. So unless you have a very powerful computer, the one rule to rule them all rule is going to take a long, long time. But you can check out in the usr/share folder on the default Kali install for the different password rules that are available. There's quite a few, and they can really help you to like develop an attack against a password hash. For instance, in Capture the Flag we've seen before, there's been a challenge where you needed to essentially like find all the passwords that were like Mario characters, and there was some hint like given, or like one of the passwords was in RockU or something, but for the rest of the hashes they weren't in RockU, so you needed to run a rule against the list of Mario characters in order to find the remaining passwords for the challenge. So yeah, check it out on the Kali website, kali.org/tool/hashcat. Very powerful password cracking tool. We've also got John the Ripper, which comes pre-installed on Kali. John is a bit older than Hashcat. The biggest difference between John and Hashcat is that John has the ability to crack zip files and PDFs and many other file types. John is an absolutely gigantic program with so many different options. If you run john-help, you're going to see exactly what I mean. I'm pretty sure you're going to get a big list of things that you can do. But in John, you can do essentially the same things that you can do in Hashcat when it comes to attacking password hashes. You can do the word list attack, pretty much the exact same as the Hashcat command, a little bit different syntax. You can do rule-based attacks, again, same idea, just different syntax. And then you can do the unique to John stuff like zip to John to crack a zip file, which essentially will get the password hash from a zip file, run the password cracking against that hash separately from the zip file. Once it finds a hash, it will then use it to open the zip file for you. This comes pre-installed in Kali. If you want to learn more about it, check out kali.org/tools/John. We'll try and dig into this John and Hashcat in the workshop section here. So we also have offcrack. And now offcrack is used to crack Windows NTLM passwords. It's a little bit janky. I've only ever really been able to get it to work on Windows, and finding these XP password lists is a little bit of a technique. I'll post the links for them in our Discord server. Yeah, I'm pretty sure they're on like a MediaFire file share site. It's super sketchy, and I'm also pretty sure offcrack will will flag your Windows Defender if you download it. So I know that it's not malware, but yeah. There's a lot of other password cracking tools too, like CrackStation, hashes.com, or passwordgenerator.net. These can help you kind of generate hashes or like determine what hash you're looking at. Like if you don't know, like let me just scroll back up here. You shouldn't ever be expected to on a glance recognize that this is PDF password hash Acrobat 10-11. There are tools online where you can plug these hashes in and it will let you know what format the hash is in, which can help you run your attack using John or Hashcat against that particular hash. I'll post these slides in the Discord. All the links in there will be clickable. So like I was saying before, creating, like with the Mario example, creating your own word list can be very beneficial to shortening the amount of time that you spend password cracking, because running the one rule to rule them all with Hashcat on RockU is going to probably set you back like 40 or 50 days, if not more, in terms of cracking. And usually during Capture the Flags, you're only going to have like 2 days. So if you're running your tool and it's telling you it's going to take 30 days or more to finish cracking a password, you might want to try to create a word list based off of hints in the challenges or other passwords that you found in the competition to narrow down what you're testing. So you can create word lists using a tool called The Mentalist. I've never used that one. I've used Crunch and I've used John the Ripper to create it. You can also just create a Python script to quickly make up your own. For one of the challenges that I did in a past CTF, we had like a list of password hashes, and we were told in the question that they were going to be like EA games. And so what I did was found a list of every EA game ever made, I think from Wikipedia, and just grabbed it off the internet and ran a rule against that in order to find the password. So really read the questions that you're looking at and also look at the other challenges in the same categories that you've been given. It can really give you a clue as to what you might be looking for. So that's going to be it for the password cracking introduction. And now we're going to move on into log analysis. I don't know if there's any questions at all so far. Let me just check. Yeah, I don't think that there's any questions, so I'm just going to keep moving on here. We just have the one more section to get through, log analysis. So completely different from the other two categories that we're covering. Once again, I'd just like to repeat the purpose of these videos is to just introduce you to all of the ideas that you might run into in a capture the flag competition, not necessarily to master each of these in the short amount of time and limited amount of information I've given you. So let's just talk about log analysis a little bit. So what is log analysis? It's reviewing computer-generated event logs to identify bugs, security threats, or other risks. There's a lot of reasons to look at logs in cybersecurity, such as compliance of your systems for security policies, troubleshooting your systems, doing forensics or incident response, or even just understanding user behavior. What was, Tom doing on Saturday? Let's look at the logs. So, what are in the logs? Well, we've already talked about network traffic analysis. Those are a form of network logs. So, we can look at the packets traveling back and forth between interfaces. We can look at software application logs. We can look at which will give you warnings and debug information depending on how much logging the software or application has enabled. We can also look at system logs, which are going to give you like network events, directory events, timestamps, security events, user creation, etc., etc. It all depends on how much you actually have turned on in your system as to what's going to get logged. So ideally, everything that gets logged would have like a format, that you could easily parse. But I think from what I've seen, there's a lot of different ones. There's lots of structured, semi-structured, and even unstructured logs. So looking at structured logs, we can talk about JSON, which is pretty much like a Python dictionary. You have your key value pairs. Windows event logs, which are very structured, as in they're going to give you certain information laid out every time. I'm not sure if Windows event logs are actually JSON or not. Maybe some are, maybe some aren't. It's hard to say. There's the common event format, which is common on Unix systems. The common log format, again, same thing. In fact, there's a picture of the common event format on the right of the screen here. There's the extended log format, there's the W3C extended log file format, and more. The point is, knowing the structure of the log file is going to allow you to get the information out of it more easily and manipulate the information more easily. Capture the flag challenges when it comes to log analysis are all about the data manipulation. They're going to be asking you stuff like how many users tried to connect at this time, how many unique usernames were used, stuff like this. So being able to identify the log type and pull information out of it is very, very useful. You really want to have logs that are well structured so that it's easy for you to parse them. So going back to last week, we were talking about network traffic analysis. Again, Wireshark is a great tool to do this. But if you know exactly what you're looking for, you can write a script using T-Shark or even use PyShark, which is a Python wrapper for T-Shark, to put in the query for the bit field that you're specifically looking for. So if you want to know it, like you want to find DNS records that were sent back and forth in a network traffic capture, that's something that's fairly easy to query for. So you might not need to open up Wireshark to actually get that information into its own log file or into its own capture file if you're able to just write a query using T-Shark or PyShark to extract that data from the log and manipulate it as you want. Like I said, from last presentation, I had a slide in there that just talks about how you use Boolean operators in Wireshark. And so that will be very useful for you if you're looking at doing log analysis with Wireshark. So ideally, like I said, you're going to get a very structured and nice looking log. So for a quick and dirty solution, why would you ever leave the terminal to like parse the information from that log? You can stay in the terminal and use Unix commands like awk, sed, grep, unique, word count, sort to process text log files easily and quantify data fields to find solutions quickly, or in the case of capture the flags, find the flags quickly. awk is a very large program, and actually within it is its own like scripting language, so it's got a bit of a learning curve, but just for quickly pulling data out like quantifying the amount of connections made or unique IP addresses, it can be very, very useful. And we'll take a look at that in the workshop section of the presentation. Looking at JSON files is a little bit different though. You're not going to want to be using common terminal parsing tools like awk and sed for JSON, because JSON has a very structured format. What I would recommend is using the JSON library in Python, import JSON. Essentially, what you can do with it is turn your JSON into dict structs, and yeah, it just makes it super, super easy to look through JSONs. You can, you know, search for all of the keys and all of the values under those keys super easily using that library. Of course, there's also Excel. I mean, love it or hate it, Excel is a super powerful tool and can do pretty much anything that you can do in the terminal, but with a nice GUI. I personally don't use Excel that much, but I know people who do, and people who can do insane things with Excel. So essentially, when it comes to log analysis, just do whatever you feel is the easiest for you to get the data that you need out of the log file. Of course, you can also just dump your log file into CyberChef. CyberChef can give you some good suggestions as to what to do with it, or even decode certain bits of it for you. And if you really want to go deep into log analysis, you can set up your own services such as Splunk or even the Elasticsearch Logstash Kibana stack. Those Splunk and Elk are going to be like some serious projects for you. I think the Security Onion VM comes with Elk already running, but if you want to do any sort of customization, this is sort of like a project. Whereas, you know, with Wireshark and with Python and terminal tools, you know, and Excel, you know exactly what you're getting into. Elasticsearch Logstash Kibana has a bit of a learning curve. It's a bit different, but it's meant for ingesting log files. So here's a picture of a log file that my server was displaying last week when I was getting this presentation set up, and I realized that I had left SSH on, and or SSH open anyways. And so what is happening here is that even though I only accept private keys to, or you know, public key crypto system to connect to SSH, people are still trying to fuzz the user and password. The log file that I'm going to show in the workshop is actually like 4 megabytes, but it's kind of a problem because I left this running for months. And so my poor little cloud server is actually just like filling up in storage from SSH logs because I left it open. But yeah, so that is our presentation portion of tonight's kind of event. So we went through kind of the basics of cryptography, password cracking, and log analysis. And now I'd like to just end the recording, and we're going to take some time in the Discord to answer some questions and do a little workshopping. So thanks for watching.